Hi everyone, this is Lakshmikant from KGP Talkie. Today we are going to benchmark Qwen 3.8 flash model, which is also supposed to be Qwen 4 model on a CPU. Later on, I'll be also showing you how you can also offload some layers on a GPU so that you can actually improve the overall generation speed. As you already know, this model comes with 180 billion parameter. This is literally huge. And out of this 180 billion parameter, there is 125 billion, which is actually coming from the model only. All right. And the remaining which you have here, almost the 30 billion parameter, in fact, the 50 billion parameter, 50 or 55 billion parameter, that is actually coming from a table which is known as embedding table, or you can say that that is the lookup table. Apart from that, out of this 180 billion parameter, 6 billion parameters are only the active parameter. Alright, now let me give you a sneak peek that what you are going to see in this particular lesson so that you can get yourself prepared. So let me first tell you first of all what kind of laptop or desktop configuration I have currently with me. So I have a 96 GB of RAM. Obviously you might not have this much of the RAM. So if you don't have this much of the RAM in your laptop or computer, then don't worry about that. You can watch this video to understand the fundamentals. Apart from that, I also have one RTX 5090 as well. Later on, I'll show you how you can actually move some part of your model on a GPU to get the maximum performance out of that. Alright, now let me just quickly show you here how much speed we are gonna get. Thereafter, I'll take you through the technical journey. First of all, I want to tell you here on my laptop, which have 96 of GB RAM and 32 GB of RTX GPU, basically the VRAM. So this is 32 GB. So 4-bit cannot run at all. 1-bit can run, all right, and 2-bit also can run. So I tested 1-bit and 2-bit. This is what you are currently seeing is running purely on a CPU. There is no GPU involvement at all. You can still see here I'm getting 10 to 11 token per second generation speed, which I believe is pretty much good and decent. Thereafter, I actually offloaded some of the mixture, the experts, basically some of the experts on the GPU. Thereafter, here I got a better generation speed. So for a 2-bit plus GPU offloading, I got around 43 token or 44 token per second generation speed. And when I used 1-bit with GPU offloading, then I got here a 52 token per second, which is literally high. Apart from that, one more thing here you will notice here, this is coming when you will do the misconfiguration. So remember this one. So this will come if you do any kind of the misconfiguration. So remember this. All right. So you just cannot offload any random layer on the GPU. So you have to be aware that how many layers you need to offload and how you need to offload. So these things we are going to cover in this particular series. Now let me first tell you my the setup here, what currently I'm using. So currently my desktop have here Intel Ultra Core 9 285K processor. That processor have total 24 core here. And this is literally important. Later on, I'll show you how processing speed changes if you bring the more cores on your CPU. Thereafter, there is 8 performance core on this Intel Ultra 9 processor. And then there is 16 efficiency core without any hyperthreading. Overall memory, it has 96 GB. Then I have here NVIDIA RTX as well. And it is running on a Windows 11 Pro. I wanted to share all these information so that you can have the best information with you to reproduce this result. And yes, I completely agree with you guys that you might not have this high-end computer with you. So obviously you cannot run this benchmarking on your computer. But this doesn't mean that you are not gonna learn anything from this particular video. Even though if you don't have these high-end computer, but still you can watch this video and you can learn the fundamental that how this model performs on various cores how this model performs with the various sizes of the context window and the KV cache, and what is going to be the generation speed, how offloading happens. These are the technical fundamentals actually which you can learn irrespective what kind of a computer you have. Why I'm telling this, you guys, let me just show you actually a comment, basically not just a single comment. I have got here so many comment, and I don't think guys it is right. All right, because I see here many people just talking here some rubbish things that why I'm doing this testing on this particular GPU and with this particular kind of the system. So see, guys, I need to just tell you here, this is the system which I have, and you know, obviously, as you know here, I just cannot own every possible GPU, and I just cannot test it on every kind of hardware configuration, right? So it is natural for me. If I have an RTX 5090, so many of my test is going to be based on my RTX 5090. And I yes understand this. Sometimes a few people get frustrated about this and even start trolling or abusing me. But honestly, I don't care about those few people. What matters to me is the thousands of the people who genuinely watch, learn, share their opinion and support this channel. So if you are one of those people, I need your support. Subscribe to the channel if you haven't already, like this video, comment your thought, your requirements and so on, and let other people know that you really liked this video and you are supporting to me. And thank you so much. Let's go ahead and get started with the main content. So as I told you, this is going to be the setup which I'm gonna use for my benchmarking. Apart from that, one thing I also should tell you here, I had to actually make this build from the scratch. I'm not saying I build the model. So the model was there. Basically, I needed to build the model so that I can run it on my computer. So I had to build it for two reasons, because I wanted to build it for CPU alone, and also I wanted to build it for the GPU as well. Why? Because by default, if you try to run on the llama server or llama.cpp, then it is automatically going to use the GPU part. So you have to make sure you build it without GPU. Otherwise, it will automatically use the CUDA behind the scene and you might not know. So all these precautions I have already taken while doing my benchmarking. Okay, now let's go ahead and see why I cannot use the 4-bit build. As I told you earlier, I cannot use this 4-bit build because the memory requirement is too much here. So currently memory requirement is like 111 GB, and if someone have 111 GB or so, that person definitely can test it. Otherwise, in my case, I have a maximum memory that is going to be the 96 GB. What is this? Somehow something got clicked. So I have here a 96 GB. That means I can use these models. I'm not gonna use here 3-bit model, because again this is going to be too tight for me, because anyway my system needs operating system and some some memory requirement for the KV cache as well later on once it starts generating the output. Because of that, I tested here 1-bit and 2-bit only, and not just this Qwen 3.8 flash next model, but I also tested 1-bit and 2-bit for Qwen 3.8 27 billion parameter model as well, so that I can show you the comparison as well. Now the question comes in here, why we still need, the question comes in here, why we actually need 72 GB even if we are using here 1-bit. This is literally huge, the huge statement here. Why? Because if you notice here, the memory requirement when we come from floating point 16, all right, so FP16, at that time the memory requirement was the 360 gigabyte, and if we come here, the Q4, then the memory requirement is coming here 111, all right, so GB. So you can see here it is almost how much? It is like 1/3, all right. So it is 1/3 actually. We actually reduced our precision by 4, and the memory requirement got reduced by here 1/3. All right, so it was 1/3 here. All right, so the 1/3 here. Then why this 1 bit is still taking this much of the memory? So ideally, then what should happen here, if we are coming back Q4 to Q1, that means 1/4 of memory. Basically, the precision we are going to reduce to 1/4, then the memory should also reduce by 1/3. But it is not gonna work in that way. So that is what I'm gonna explain you here, why it doesn't work in that way. Because if you go here bitwise, then this overall, the parameter which we have, total 180 billion parameter, that should be fitting with the 22 GB only, but that is not gonna happen. All right, so it is going to take how much memory? 72.5 GB of memory. And where all these memories are going to be by whom all these memories are going to be taken? So these are the part of the model which is taking this much of the memory. So this is what I was telling you earlier. If you are still watching till now, then you understand here why I was telling you that even though if you cannot run this on your hardware, you are going to learn a lot of things in this particular lesson. So these are the technical, all right, so these are the technical things, these are the fundamentals which you need to learn, whether you have laptop, whether you have desktop or not. All right, doesn't matter at all. If you really want to learn the fundamental, then obviously you have to complete this video. Okay, so MOE expert here. So this is the mixture of expert, the mixture of expert layers and the blocks. They are taking most of the memory. So the mixture of expert is taking 37 GB of the memory, and that is coming like a 55% of the overalls here. And most interesting part is going to be this one. So this is the table which I was talking earlier. So this, you can say the embedding table, or you can say the lookup table, which is used to get the static embedding. So this table is actually taking how much? This taking a 40% of the overall memory requirement. That is like a 27 GB. Out of 72 GB, it is taking 27 GB. And to your surprise, you can see here, there is only one tensor. Only one tensor means there is only one vector. And that vector is actually taking this much of the memory. Tensor is much more complicated than the vector. So I'm just simplifying this. So basically there is just one single tensor, and in that it is going to consume almost 40% of a memory. Now the question comes in here, if it is 1 bit, then how it is consuming this much of the memory? So actually it is not 1 bit. So it is actually the 4 bit. Okay, why it is 4 bit? Because this is the embedding layer. Okay, so this is embedding lookup table. So embedding lookup table performance actually decreased drastically if you reduce it to the 1 bit. That is why Unsloth team, from where I had taken all these weight, Unsloth team said, okay, we cannot do it with the 1 bit. Let's go ahead and keep this embedding table as a 4 bit, and rest of other things we can reduce to the 1 bit and 2 bit and so on. And apart from that, the full attention and Qwen sparse attention is taking 1.7 GB, which is just about 2.5%. And then the everything else is taking almost the 2 GB, which is like a 3% almost. Now you understand from where this particular memory is coming. Okay, cool. Let's go ahead and visualize this with the table here again. So the same thing as I told you here. So this is where all these, this is where all those memories are actually going. Okay, great. Now let's go ahead and see, when I tested this model with CPU only and with the RAM only, which I have 96 GB of RAM, actually DDR5 RAM. Okay, so I have here DDR5 RAM. And also if you want to know my RAM configuration, so it is DDR5 RAM, and it was CL22, and megahertz speed was, I guess, 6400 megahertz, or it was 6600 megahertz. So exactly I don't remember how much it was actually. So it was this much only. Okay, cool. If you need more information, you can just comment in the video. I would be more than happy to tell you about the further configuration. Okay, great. Now, if you remember earlier, I told you that my computer have total, basically my processor have total 24 threads, or 24 actually the core. Okay, so at that time I raised a simple question that whether the CPU cores are gonna help in our generation speed or not. My question, I mean my question was straightforward, and my answer is here also a straightforward answer is no. If you increase the GPU, if you actually increase the number of CPU core, then the generation speed is not going to increase after a certain limit. Now you are going to find out the answer here, why that is not going to happen. But before that, let me just explain you here the table. Instead of explaining the table, let me just show you here with the figure actually. Otherwise, if you find it simple with the table, you can see here. So here the number of threads here. So basically the number of CPUs there in my computer currently running. So if I have a 4 CPU only, 1 bit generation is like 7.5, 2 bit generation is like around 8 only. When I'm using 8 thread while generating, then I'm getting 10 token per second, and thereafter you are going to see here it is flat here. Now let me just explain you through the image here. So when I moved from 4 to 8, there is a little bit improvement. Thereafter it is going to be flat here. Okay, so do you see here what is happening here? Even though we are actually increasing the number of threads here, basically the number of CPU, our generation speed is not going to increase. Okay, so this what you are seeing here, this one is actually the generation. So I'm talking about the generation speed. And what you are seeing here, this is a filling. All right, so this is prompt decode, or you can say that. All right, so when you give inputs to your LLM process those input. So this is input processing speed. All right, so input processing speed started with the 20 token per second, thereafter 35, 38, and then it kept increasing. So two things are coming here. Input processing speed is increasing here, increasing here as threads are increasing, but output generations are not increasing. So the question is here, why? Because input decode or input generation, so there is no actually the generation in the input, so it is just like input processing. So input processing is directly proportional to the number of threads you have in your computer. Why? Because it is computational intensive. So this is the computational things. All right, so this is computational things here. But in this case, what happened, most of the things are going to come from the RAM. So this particular thing, what you are currently seeing here, this is limited by the RAM speed. All right, so whatever RAM I have here, CL32, and I'm assuming it was the 6600 megahertz. Because of this, actually, because of this generation speed is limited. That means if you increase the number of thread in your processor, that is not ultimately going to increase your RAM speed. So if you have higher RAM speed with the same processor, then you are going to get the better generation speed. Okay, that is why I told you guys you need to watch this video to understand the fundamentals. Again, if you have learned something, please do not forget to comment what you have got, and just tell me that at this particular point you are watching, so that I can understand that, you know, my encouragement and my ask was helpful to me, and you really commented after listening this. Okay, having said that, let's go ahead and then see then how this RTX 5090 is going to help us. So I guess till now you must have got the idea that the generation speed is not limited by the CPU computation, but it is limited by the RAM speed actually. So in RTX 5090, what happened here? So whatever the memory this has here, 32 GB, that is actually known as a VRAM. All right. So this VRAM which you are seeing here, this is literally very fast VRAM. Okay. So its memory bandwidth is extremely high, because in our PCI 5 where we have a DDR5 RAM, their bandwidth is not that much. That I mean, those memory bandwidths are not that good as the RTX 5090. I don't remember exact memory bandwidth, but I can guarantee that there is like the 100x difference, or even maybe more than that, between the normal RAM memory bandwidth versus the RTX 5090 bandwidth. Okay, so what we do here, we have got a 32 GB from our RTX 5090. You might have here other GPU as well, maybe RTX 1580 or 5070 or maybe RTX 4060 or any GPU. What you need to understand from this topic, that you need to understand how you can offload some part of your model on the GPU so that actually you can improve the generation speed overall. Okay, so before we move ahead, let me just tell you some fundamental about this, basically about this particular model. And if you have not watched my previous video, let me just tell you here. Previously, when I was covering Qwen 3.8 flash next video, at that time I explained this model architecture in detail, and also I explained that how many experts are there and how many layers are there. Okay, just to refresh that part, I want to tell you here, there are total 48 blocks there. All right, so you can see that there is 48 layers. Okay, and in each layer you are going to have here 512 experts actually. All right, so 512 experts are going to be there in each layer. So now if you multiply all these together, then you are going to get the total number of experts available in this particular model. Okay, so now what we can do here, we can actually move some of these layers inside the RTX 5090. Apart from that, if you have remembered our previous conversations, when I told you where all those, what part of the model was consuming all this memory. So if you remember this part, in fact, I'm showing you here. So you are going to see here, this is like 1.7 GB and almost the 2 GB. If you combine all these together, so they are like, I guess, 3.8 GB. All right. So the full, the full attentions, Qwen sparse attentions and everything else there is going to be the 3.8 GB. We can actually offload this to the GPU. Okay. Apart from that, some part of this expert we can also offload to the GPU. Let's go ahead and understand that how much we can actually offload to the GPU. So I'm going to first here explain you. So the one thing we now know, 3.8 GB, which is coming from the, the full attentions and Qwen sparse attention, we can move that on the GPU. Now out of 32 GB, which I have with my GPU, how much is left here? 28 GB is left here. Okay, so 28 GB is left now. Now what we can do here, we can start here layer by layer movement on the GPU. First of all, I'm going to tell you here, when I do not move any layer at all, and I just move this particular part which you are seeing here. All right, so attention and Qwen sparse attention, if I move to the GPU and rest of other things are going to be on CPU only, at that time my generation speed got improved here, and this was like a 3x improvement. Why? Earlier we used to get like 10 to 11 token per second speed with the pure CPU. Now by moving this part only, by moving this attention part on a GPU, I got a huge improvement, 3 times of the improvement. Okay, when I moved 8 layer of GPU, remember per layer of GPU is going to have how many expert block? 512 expert blocks were there per layer. All right, so per layer. So the total I'm taking here 8 layers. Out of how many layers? Out of 48 layers. So I took 8 layer and then I moved that on GPU. Now my token speed has gone from 30 to 36. Thereafter, I kept increasing layer by layer. By the time I reach 32 layer, my 1-bit generation speed got here the highest one, that got around the 51.97 token per second. But in 2-bit generation, you are going to see here on a 32 expert layer, it is actually like 5.5 token per second. So it actually reduced drastically. Why it is happening? Because you see here 1-bit generation is not taking that much of the space. In 2-bit generation, what happened? By the time you move this 24 layer on a GPU, all these available memories are going to be filled. Now, if you try to fill more, here more expert layers in the GPU memory, then ultimately your GPU is going to actually offload those on the system RAM. So again, that is going to make it slow. So basically that is not good thing, and this happens in the Windows only. So Windows actually does not throw the the memory overload or something like that. Basically silently they shift GPU memory into the shared memory space. Because of that, this sudden drop you are seeing here. So if you are feeling, I mean, if you are also seeing a similar, the drop in your testing, then you can understand here you are actually leaking memory. Basically, your GPU is not able to handle all memory by itself. So your weights are actually going into the shared memory. Okay, cool. Now I hope you have understood this. Okay, so this is what I explained you. I explained you what happened actually. Now the question is here that how fast it is gonna generate when you are going to fill some context. Basically, let's say you start chatting with the model. After some time, some context is already filled. By default, this model comes with how much context? If you remember, it comes with 264K tokens. Total context window is here. Okay. So let's say if some part of the context is filled, then how it is going to affect this generation speed. Then I tested this particular part. So I tested this part and I found this result here. So in 1 bit plus GPU, overall token speed was around the 50. But as I start filling the context, my token speed got decreased here. I mean, it started decreasing here. Similarly, in 2-bit GPU, the token speed also started decreasing. And similarly, in a CPU as well, when only CPU I used, at that time also I see my token speed started decreasing here. So you can clearly see here, a little bit decrement was there, 0 to 4K context. Thereafter, a linear decrement is coming. And I guess it is not much, 15% decrement is like acceptable. And overall, I see here it is quite acceptable range here, 15 to 22%. 22% is little bit high, but 10% is fine. I have seen many models which actually decreased drastically, not just 10%, 15%, but I have seen many model actually who used to decrease like 60 or 70%. Okay, great. Now here is my question to you. So it doesn't matter how fast your model is if your model is wrong. So to understand that, what I did here, I actually also performed that testing part here as well. So first I did here Perplexity test here. So Perplexity is going to tell us that how good our text generation model is. And to my surprise, I see here this particular model, this large model, which is actually compressed in 1 bit and 2 bit, is literally much better than the Qwen 3.8 27B with the 4 bit. Okay, you can see here. So in the Perplexity, lower the perplexity, that means better the model. Okay, so you see here this particular model, Flash Next 180B model here have just 2 bit and 1 bit. Its perplexity is like 4 or even less than that. But you will notice here Qwen 3.8 27B model with the 4 bit actually. All right, so this is the standard model now we use here every day, daily. I mean, nowadays actually we use this, and its perplexity is 5.68, and this is literally high. So I can say here that this particular model, which is crushed to the 1 bit and the 2 bit, basically it is compressed to the 1 bit and 2 bit, this model is literally performing much better than the full-fledged Qwen 3.8 27 billion parameter with 4-bit quantization. All right, now, so this was the perplexity. I also actually tested this on the real questions as well. So I asked here questions related to the math, I asked question related to the code and also the reasoning and so many other things about, and I got the answer even in 1 bit of the model, and it was literally fast, and it was able to answer it immediately. And also I want to share here one fact about this here, what kind of answer actually I got. I'm just trying to find out if I have that here. Yeah, here I have here. So I actually used 1-bit quantized model of 27 billion parameter model to understand how their answer is going to be here. Okay, so here is the answer. A simple question was there, like who invented the transistor? And answer was like this here. So Bell Lab was fine. Nobel Prize in 1956 is fine. Thereafter, you are going to see here all these names. So they are a faked name. So basically, this particular model hallucinated so well that if someone does not know, the person can believe. And I'm talking about the 27 billion parameter model with 1-bit quantization. But if I use the Flash next model with 1-bit quantization, the answer was exactly the correct. So this is also correct. All these people name are also correct. Scientist names are also correct. Nobel Prize is also correct. Everything is correct here. Not just this one. In fact, I tested this coding and everything else. I saw that 1-bit, 2-bit, and then 4-bit, this one, they were able to perform better. Obviously, I did not set very the hard problem statement here intentionally, because that was not my intention at first place. I wanted to understand the speed, I wanted to understand its perplexity, I wanted to understand its the general knowledge, I wanted to understand how the kv cache is gonna affect. So I wanted to understand all of this. Apart from that, I also wanted to understand how actually I can speed the generation, the token generation speed, how I can actually increase the token generation speed by offloading some part of the model into the GPU. So all those things I have tested in this particular, the benchmarking tutorial, and link for this tutorial is available here on the kgptalkie.com, and also the link of this tutorial is available in this video description as well. All right, everyone, and please do one thing: like this video, comment if you are still watching. Then I'm sure you have, you have really liked this particular video. So please do not forget to subscribe this and share it on the social media as well. All right, everyone, bye bye, take care.